So we're going to continue with Chapter 7 and Section 17.2, which deals with sampling distribution of a sample proportion. The majority of the notes we're going to do in class. We're going to do a class activity and then several examples. I want to give you an idea of what we're now shifting gears into. So we have this concept of what a sampling distribution is, which is really a distribution of all the possible p hats or x bars that you can get. So in particular, today we're dealing with proportions. So the activity that we're going to do in class, which I want to give you a preview of, looks like this. So we're dealing with the percentage or the probability of getting an orange Reese's Pieces. Okay, and we're taking samples of size 25. So we know in our population distribution, 50% of the Reese's Pieces are orange, 25% brown, 25% yellow. So that's what's true in terms of our population. But we're taking samples of size 25, and we want to see what we're going to get in our particular sample. So when we go ahead and we take a sample from that population, we're getting a p hat value. This particular p hat value that I got was 0.52. When we're talking about a sampling distribution, we're really creating a distribution of every single possible p hat that we can get. So we're doing an infinite many times of what I just did. So I'm not taking one single sample or two single samples to get those p hats. I'm going to take an infinite amount. So I'm going to take maybe 1,000 samples here. I don't want to animate all of those, but I'm taking 1,000 samples here. And that graph that we're seeing now down here, this is a simulation of what the sampling distribution is. We're plotting each of our individual p hat values. So I got p hat values, meaning sample proportions as low as 24% or maybe even 16% orange and as high as 84% orange. Okay, but notice where they're centered. And this is the crucial thing for you to start to think about. Notice that my distribution is centered at about 50%. And if I go ahead and I take a summary of that, meaning I take an average of all of my individual p hats, which is what this graph is, notice that the average is almost exactly equal to the population proportion. And if I took even more samples, so now I took another 10,000 samples, notice what my actual mean is. And this mean is the average of all of my individual p hats. And notice that the average of all my individual p hats is 0.50. The standard deviation is 0.10, okay? So these two values are very, very, very important. One thing I want to note, okay, what if we changed our sample size? And I wanted you to, in particular, look at the standard deviation here. So instead of taking samples of size, say, 25, let's take samples of size 200. So I'm going to reset, and instead of taking a sample of size 25, I'm going to take a sample of size 200. Just to show you what I'm doing here, so again, from my population, I've just taken a sample of size 200. In this particular sample, I got 46% were orange. And I'm going to do this, again, 10,000 times. And they're going to plot down in here my individual p hats. Notice once again, the shape of the distribution, similar to the last shape, was symmetric and can be argued that it's approximately normal. Notice that the mean, meaning the average of all my individual p hats, is still 0.50, but notice what happened to my standard deviation. When I increased my sample size from 25 to 200, notice how the standard deviation drastically declined, okay? And notice my most extreme samples that I got. Before, remember, I had samples as high as 0.84 and as low as 0.16. Here now, all of my individual p hats were somewhere from maybe 0.36 or so to about 0.6, somewhere in that range there. So notice how when we increase the sample size, we decrease the standard deviation. We're going to talk more about this in class and go through an entire example as we do that. But I do want you to get a couple things down in the notes. So those things are on page 9. So if we go to page 9, first thing, when is it acceptable to say that the distribution of p hat is approximately normal? So that depends on n and p being large enough. We have this very important condition which we're going to see lots from now until the end of the course. For proportions, we have what's called the large counts condition. And that is n times p greater than or equal to 10 and n times 1 minus p, meaning taking your sample size and multiplying it times the probability or the proportion, and then the sample size times 1 minus that value. If both of those values are greater than or equal to 10, then we can make the statement that the sampling distribution is approximately normal. In addition, we have some formulas for the mean and the standard deviation of the sampling distribution for a sample proportion. These formulas are all on the formula sheet. First one, we have mu sub p hat is equal to p. Well, what does that mean? That means exactly what I was just showing you. The mean, mu, of all my little individual p hats, if I average all of my individual p hats, that's going to be equal to the mean of the population proportion. So again, if we go back here, when I average all of my little p hats, which is what this value is right here, the average of all my little p hats, notice that it's equal to the actual probability of orange, or the actual parameter value. That always happens. Your formula for the standard deviation of the sampling distribution, sigma sub p hat is equal to the square root of p times 1 minus p over n. And as we saw, as n is increasing, the spread is decreasing. As we increased our sample size from 25 to 200, the standard deviation, or the spread of my sampling distribution, has decreased. In order to use this formula, that same independence condition that we saw in the last chapter, our sample size needs to be less than 10% of the population size. So to reiterate what the sampling distribution of a sample proportion is, it is all of the possible p hats that we can get. The mean of the sampling distribution is equal to the population proportion, and the standard deviation can be found using the formula here. We'll go through several examples in class, including going more in depth with the Reese's Pieces. I'll see you then.